first movement, which is complex movement. The complexity of movement data is often gestures to seek out methods that avoid its complexities rather than embrace them. So I've decided, maybe foolishly, to embrace the complexities of movement. Now, in the simplest way possible, which is to model it in terms of, or not model it, but just take recourse to complex numbers. And complex numbers, are some of you are familiar with it. They're basically just a way of sort of bookkeeping. Every number has two components, a so-called real component and an imaginary component. And so every complex number represents a vector. And that vector can be very easily represented in terms of its length and its angle. And so already you feel that it's sort of an intuitive way to think about movement. Because it's already sort of in a kind of natural language of lengths and angles. You can do things to complex numbers. You can add them. So you see, as we add them, two vectors add up. And then there's this thing. This is kind of an important concept. This is a product of a number and its complex conjugate. And all that does is it's sort of a measure of how similar two angles are. So if two angles are identical, then this product is going to be a real number. If two vectors are perpendicular to each other, as they are here, then it's a purely imaginary thing. And so it is somehow a measure of how similar two vectors are. And we're going to take advantage of that to sort of create a autocorrelation structure to see how similar velocities, neighboring velocities are. So if we, let's get the slide. So this is a movement, and we can measure these velocities, and we take the complex conjugate product of these neighboring points at some interval tau, and that gives us this autocorrelation function. We take the average of that over the whole thing. And so obviously if tau is very small, we're multiplying two vectors that are identical. It's some positive number, and if they're very different or unrelated, then that average is going to be about 0. So it's a complex velocity autocorrelation function. And so this is going to be our tool. Now this is a model. This right here is a stochastic differential equation in complex variables, which isn't something you'll see too much of, I think, in most ecology talks. But it's really not that bad. I'm not going to go too much into details, but it has three important parameters. This alpha parameter tells you how a velocity is rotating and how it sort of relaxes to a mean. This mean component is this sort of advection, sort of a mean movement, which is something correlated random walk, by the way, cannot capture. It's just advection or rotation. And beta is some strength of randomness, and W is point noise. So this should give you an idea. This is so at a certain parameter set, you can just get a random walk. It's just a random walk. With other parameters, you can get a nice correlated walk. Right? And again, that alpha. So that alpha is really kind of sort of an index of correlation. If it's real, it sort of tells you 1 over alpha. It tells you something about the time scale of the relationship between these points. If we look at oops. So, and then if you have an imaginary component to that thing, then we get this loopy thing. It's still random, but it's loopy. Right? Again, something that you can't really do with a correlated random walk. And then you can just add advection to it. And you get this kind of loopy, advective beast. But it's also kind of random. I mean, it's still a stochastic process. So, basically you can get kind of forms for that autocorrelation function. And it has all these parameters in it, and you can estimate the parameters just by fitting the function. So, for example, the random walk is absolutely uncorrelated. You can see that here in the complex velocity, the real part. If it has this sort of correlation at second walk, then we can sort of see that in that function. If it has loopiness, we can sort of see that it oscillates the correlation function. And if it has advection and loopiness, then it has this sort of oscillation, and it has a mean. So basically, you can estimate all the parameters. So we're going to apply this to this guy. This is a Heterosigma kashibo is an algae, second-class plant, but it has two flagella, so it makes it an honorary animal. One flagella, I don't know what it's for. The other one moves it.
They're looping.
Okay, good to know. It causes toxic tides. I don't think this is actually a heterostigmatide. I don't think it quite so red. It also moves around in tanks, and these can be digitized. So they unwillingly succumb to digitization. These are a bunch of tracks. And we can take this, and you can see sort of from the tracks that there's sort of tight coils, there's looser coils, there's kind of more or less randomness. They seem to have a lot of directionality to them. And so it seems like a really good subject to fit this sort of model too. Here's one track, this is data. This is its complex autocorrelation function that's fitted with these parameters. And here's the track that's simulated from those parameters. So we can see that we can do a pretty good job of sort of capturing, like, what is it about that track? There's like a certain amount of variability, a certain amount of loopiness that we can capture in sort of advection. So that works. It works well. Here's another one with very tight coils. Here's very tight coils. The one thing the model as it is simply can't do is, and this obviously has some sort of larger scale directional change. Of course, we can only have one vector, but it can capture this, it can capture something that looks like that. So the point of all that really is just to say that our final report is that it is possible to do a little bit better. There aren't that many more parameters in a correlated random walk, really only one more. But we can capture a lot more versatile behavior. And this is a continuous model, which can be useful. It's very useful for applications where where intervals are irregular, where you can't assume discrete.